So now let's go to spatial mechanisms. Okay, so spatial. So up to now, all our mechanisms, the motion was in a plane. Okay, now let's consider mechanisms that can move in space. Okay, in three-dimensional space. Okay. Well, let's see. Okay, let's do the work first. So what changes? What changes? Well, if we have n rigid bodies in space, okay, and they all move independently, how many coordinates do we need? We need 6 for each rigid body, right? 3 for position, 3 for orientation. So remembering to subtract ground, okay, the degrees of freedom of a spatial mechanism would be 6 times n minus 1. Okay. Now, if we have a joint connecting 2 rigid bodies, what does it do? If it's a 1 degree of freedom joint, it reduces the number of parameters from 6 to 1. Okay. If it's a 2 degree two DOF joint, it goes from 6 to 2, right? So we would have something like that. Okay. So the only thing that's changed here is that we've replaced 3 by 6 for the spatial version. Okay. All right. We can simplify this a little bit. N minus 1 minus j plus I from 1 through j fi. Okay. So the reasoning is exactly the same as for the planar case. Okay. But now we just remember that a body or link in three-dimensional space requires 6 coordinates, not 3, but 6. Okay. So that's why 3 becomes 6 here. Okay. So here's our formula. All right, let's do an example. Okay, so this is called the 6 UPS platform. Okay, so here's what it looks like. Okay, we have an upper platform and a lower base. Okay, so this lower base is fixed. Think of it as ground. And there are going to be 6 legs connecting this upper mobile base with the fixed base. Okay, so we're going to draw, let's draw U-joints up here. Okay, 1, 2, 3, 4, 5, 6. Okay, so we have 6 U-joints. And at the base, we have 6 S-joints. 1, 2, 3, 4, 5, 6. Okay? Now we're going to connect like that. Okay, we have 6 legs. And each of these legs, the length can be adjusted through this prismatic joint. Okay, so this is a universal joint. This is a P joint. This is a spherical joint, shoulder joint. Okay. All right, so now let's calculate the degrees of freedom of this mechanism. All right, so let's calculate the number of links first. Number of links. Let's see, 1, 2, this is ground. Okay, and then we have 6 legs, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 links. Okay, number of joints, 6 plus 6 plus 6, 18. Okay, and then the degrees of freedom. Well, this gets a little bit more involved. We have, let's see, 6 S joints. Okay, so each S joint has 3 degrees of freedom, so it's 3 times 6. We also have 6 U joints. So each U joint is 2 degrees of freedom, so it's 2 times 6. And then 6 P joints. Okay, so this is 1 times 6. Okay, so now let's put everything back into Grubler's formula. Okay, so 6 times 14n minus 1 minus j, which is 18. And then plus the total degrees of freedom of the joints. So we have 18 plus 12 plus 6. Okay, so it's 18 plus 12 plus 6. Okay, so if you do the calculation, comes out to 6. Okay, 6 DOF. Okay, so that means you can control 6 joints independently. Okay. Now in these types of mechanisms, usually it's the P joint that's controlled. Okay, so these P joints have motors. Okay, and as these legs increase and decrease in length, this platform moves. Okay. Now, have you guys tried the driving simulators in these game rooms? Okay, usually they're built on these types of platforms, right? These legs move, and you're sort of moving on top. Right? Okay, so here's another spatial mechanism. Okay. There we go. Yeah. Right. How many degrees of freedom is this? Okay, how many degrees of freedom? All right, so you can sort of. Oh. All right. Oh. Yeah, my 7-year-old boy is very impressed with this. How many degrees of freedom? Oh, you don't need to count, right? I mean, you can just you can look at it. What does it look like? Looks like 1 degree of freedom, right? 1 degree of freedom. You see? So now you're getting a feel for what degrees of freedom are, right? It's 1 degree of freedom. Okay. I think we have time for one more example. I want to do the 3 UPU mechanism. Okay, so you can guess what it is. It's basically a platform with 3 UPU legs. Okay, so here's a U joint connected together by a P joint, and also here U joint, okay, connected that, and then okay, so here we go. So we have a U joint here, a P joint here, U joint here. Okay, all right. So everybody, start calculating the number of joints and links, and let's see if you get the same answer as I do. All right, so number of links. 1, 2, 3, 4, 5, 6, 7, 8. 8. Number of joints is 9. Okay, and degrees of freedom, we have, let's see, 6 U joints. Okay, so it's 2 by 6. And 3 P joints. So it's 1 by 3. Okay. So the degrees of freedom, it's a spatial mechanism. So 6 times n minus 1 minus j, 8 minus 1 minus 9, plus total degrees of freedom, 12 plus 3. So this should equal 3. Okay, so 3 degrees of freedom. So it would seem to make sense to put motors on these joints. Okay? So if you increase or decrease the length, this platform moves. Okay? What that also means is that if I fix the length of each of the legs, okay, it should not move, right? That's what degrees of freedom implies here. So if I fix the length of each of these legs, they should not move. Okay, everybody agree with me? How many agree? How many disagree? Okay, democracy is not working here. Okay. So here's the UPU mechanism. Okay, because you refuse to vote, I have to bring a model here. Okay, so the leg lengths are fixed, right? Leg lengths are fixed. You cannot change the length of the legs. So this should not move, right? Okay, should not move. All right, all right. How many degrees of freedom you think? Right, so you got a feel there, right? That's clearly 1 degree of freedom. How many degrees of freedom is this motion? Looks like 2, right? Maybe 2, maybe 3. I don't know. It looks like 2. I would guess 2. Okay. All right. So now you might say, hey, isn't this like that planar parallelogram mechanism where all the 3 leg lengths are the same and the joints line up? Then it's a special case. Well, if you change the lengths of these legs to be different, still does this. Okay, still does this. All right, now there was a paper, I don't know, about 10, 15 years ago, describing this mechanism, saying, I have a great mechanism, it's very easy to build, it does only Cartesian motion. We read the paper, we said, wow, that's a nice mechanism, let's build it. So we built it, and it didn't work. Okay, this is what happened. Okay, so we called the author and said, hey, you know, your design, there's something wrong with that. And he says, oh, yeah, I know, I withdrew the paper. And that was it. Okay. So what's the lesson here? Grubler's formula, you shouldn't trust it. Okay, you shouldn't trust it completely. Okay. Now you saw for the planar case, it's kind of a special case. Okay, but for this, there's some strange things going on here. Okay, and Grubler's formula just does not work. Okay. This. Actually, it's more like 5. Okay. Okay. And this is kind of an open question, why this is. And there are some theories. Okay, I have one. Other people have different theories. But this is a singular mechanism. And we'll talk more about singular mechanisms later in the course when we go to the chapter on closed chains. Okay. Okay. That's all I have to say for today. If you have any last-minute questions or comments, I'll take them now. Otherwise, I'll see you next week. Okay. Thank you. See you next week.